Precalculus, lesson 11.4, logarithmic functions. Here we go. This is 11.4, logarithmic functions. Okay, log functions. Logarithms are super powerful tools for, among other things, evaluating stuff when we're trying to essentially release x from being in the exponent. So it's like, I want to solve for x, but x is in an exponent, and so it's kind of trapped there. How can I release it and analyze it and solve? And logarithmic functions, among other things, work as a tool for allowing us to do that. So logarithmic function is the inverse. I'll say logarithm is inverse of exponential. So in other words, if we have y equals b to the x, and we want to find the inverse. This isn't the reciprocal kind of inverse. This is the function kind of inverse, which graphically is a reflection over the line y equals x. So if we have y equals b to the x, and we want to do some rearranging in order to, well, find the inverse, you would swap x and y and then solve. What we would end up with when we did some rearranging is we would end up with, I want to start with that. Yeah, let's go ahead and put it this way. We get that x equals log base b of y. So I haven't done the swapping x and y yet. I just kept things as is, and I rewrote this as a logarithm. I think some numbers would make this a little bit more clear here. Let's just say if we dealt with 8 equals 2 cubed, right? 2 times 2 times 2 is 8. How this would rearrange as a logarithmic expression would be x, in other words, 3 equals log base 2 of 8. In other words, here's what we're saying. Basically, this could be viewed as 2 to what power equals 8. So what we're solving for here, the variable here, x, is the exponent. This is the exponent. So the logarithm equals an exponent. Logarithm equals an exponent. So the exponent is what we're finding. The exponent, it's like, what exponent do we need in order for 2 to the power of the exponent to equal 8? Okay? So we could say, like, a couple sample problems of what you'll have in the homework would be like rewrite as a logarithm, which is what I essentially already have there. So we could go with, what do I have? I could go with, how about 1/2 to the 4th equals 1/16. No, I'll go with this. 1/2 to the -4th equals 16. All right, rewriting this as a logarithm, we would say log base, and this is the base that's being raised to a power. So that's what we put down here. Log base 1/2 of 16 equals the exponent, -4. So -4 is the exponent, base is the base, and then 16 is what the base to the exponent equals. So this would be read log base 1/2 of 16 equals -4. That's what that would be read, end quote. Okay? And likewise, you could go back the other way. So we could also say, like, rewrite as an exponential. Rewrite as an exponential, we could go with something. So I want a log, so let's go log base 125 equals 3. Right? How would this rewrite as an exponential? Well, my base is 5. What the log equals is the exponent, so 5 cubed equals 125. This would be the exponential expression of this logarithm. Right? Hopefully that makes sense. Now let's get into some of the logarithm rules. Because what a log equals is the exponent, we end up with properties or applications or arithmetic with logarithms being the same as what you do with an exponent. So like for example, if you had b to the m times b to the nth power, what does that become? That becomes b to the m plus nth power. We have stuff like that going on. I won't get into all of the whys and wherefores of what we get on, of what we see. But that gives you a little glimpse of why some of this will happen. So we have properties of logarithms. And the first one is the product property. Product property. We could put it like this. Log base b of m times n equals log base b of m plus log base b of n. You see that okay? Yeah, I think so. All right, so that's that one. Quotient, as I mean, you could probably deduce what would happen here, but quotient. Here we have log base b of m over n is the same thing as log base b of m minus log base b of n. Yeah, that's that one. Power rule. Power rule. This one is very handy. We have log base b of m to the pth power. Well, when you have the power of a power, so here it's like if you have some base to the nth power times some base to the nth power, you end up adding the exponents, right? Because this whole expression represents an exponent, this whole expression represents an exponent, so you add the exponents. When you have power of a power, what do? You multiply the exponents, and that's what we end up having here. We end up with p times log base b of m, called the power rule. The exponent of what you're taking the logarithm of comes out around and again ends up being multiplied by the logarithm. Yeah, that's the power. And then finally, the equality property. We could say if log base b of m equals log base b of n, then we can say m must equal n, right? If it's same base to the log, then that and that must equal each other. Okay? Hopefully you can, yeah, I think you can read that fine. All right, so let's talk graphs real quick. So that's some general properties we're going to use to, no, actually, let's jump into using these properties to solve some stuff. Then we'll look at the graphs. All right. So let's do some solving of x using these properties that we know. So let's start out with, how about this? Let's solve, since we're going to be dealing with all of these, let's solve log base 6 of x, base 6 of x, plus log base 6 of 9 equals log base 6 of 54. Okay, so we got to use one of these properties. All right, well, I see log base 6 plus log base 6. So I can combine those into one log, and I can use my product rule in reverse. So I have log base 6 of something plus log base 6 of something. I can rewind that to this, and I can write this as log base 6 of 9x, or x times 9, so I'll rewrite as 9x, equals log base 6 of 54. Ooh, now I can use the equality property. I have the same base, log base 6, log base 6 equals, so I can rewrite this as 9x equals 54, divide both sides by 9, I get x equals 6, that's my answer. So in other words, 6 to what power will give me 6, plus 6 to whatever power will give me 9, is the same thing as 6 to the power that will give me 54. Or in other words, 6 to what power equals 6? Well, that would be a 1. 6 to what power equals 9? Well, that's something kind of ugly. 6 to, yeah, I mean the ugly stuff here. I mean, it works out, but 6 to what power equals log base 6? Yeah, I don't need to get into that. You get the idea that if I took 6, I took what exponent? X is 6. Oh yeah, that's basically what I'm saying. What value do you have to have here? All right, I'll just leave it there. Because it'd be 6 to the first. This would be 1 plus 6 to whatever power will give you 9. 1 plus whatever that is the same thing as the power that you would need, 6 to the whatever power you need to give you 54. Okay, so that's using that to solve. Let's look at one like this. Log base 7. Okay, here we go. Solve 1/2 of log base 7 of x plus log base 7 of 8 equals log base 7 of 16. So we have some similar stuff going on, but we have this, except for that 1/2, what we have here is very similar to what we started with. So once we get past the initial step or two, it'll be kind of autopilot from there because we're just repeating the same kind of problems what we just did. But let's see what happens with this 1/2. Now I can distribute this, right? I can say that's the same thing as 1/2, right? Ooh, you know what I might want to do instead? Yeah, I kind of like, do I like that better? Like a lot of stuff with algebra, you can do it multiple ways. But what if we did this? What if we multiplied both sides by 2? Okay, that's going to cancel, it's going to clear that 1/2. So I'm going to get log base 7 of x plus log base 7 of 8 equals 2 times log base 7 of 16. Well, I have 2 times a log. I can use my power rule, and I can say that's the same thing as log base 7 of 16 squared. 2 times the log becomes 16 squared. And here, my log base 7 plus another log base 7, I can rewrite that as log base 7 of multiply those two and get 8x. So I have 8x equals, or log base 7 of 8x equals log base 7 of 16 squared. So then I can say 8x equals 16 squared, right? Okay. Now, if I don't want to deal with my calculator or big numbers, I can say, well, 16 is 2 to the 4th, right? 8 is 2 cubed. So I can say 2 cubed x equals 2 to the 4th squared, right? 2 to the 4th squared would be 2 to the 8th. So to solve for x, I'm going to be doing 2 to the 8th divided by 2 cubed. That's going to give me 2 to the 5th. 2 to the 5th is, well, I already deduced that 16 is 2 to the 4th. Multiply that by 2 one more time, and I get 32. So 32 is the value of x there that will make this equation true. All right. Hopefully that makes sense for solving these. I'm looking for, I mean, we didn't use the quotient rule, but that's the only rule that we haven't used yet. That should give you a pretty good idea of how to deal with these. Okay, and then real quick, let's look at graphing these. I'm going to erase this left-hand side and go from there. So, nice thing about videos, if you're behind on notes, you can always just pause or rewind and get what you need there. Okay, so graphs. We're going to use what we know about graphs of logarithms being the inverse of the graphs of exponentials. Okay, so I could go ahead, all right, so graphs, we could say the log is inverse of exponential. In other words, it's going to be a reflection of y, it's going to be a reflection, take the exponential, reflect it over the line y equals x. So here's what we have. If we look at log versus exponential, the growth went from gradual to steep. Log, it's going to growth goes steep to gradual. Exponential has a horizontal asymptote. Logarithmic then has a vertical asymptote. Without translation, we have the point 0, 1, right, across the y-axis at 1. Here, without translation, we're going to go through the point 1, 0. Okay, so using what we know then, we can look at a graph like this. If we took the exponential like y equals 2 to the x, swapped x and y, solve for the new y, what we get here is y equals log base 2 of x. Y equals log base 2 of x. Second? Yeah. So if we look at comparing those graphs then, this marker's starting to run dry. Bummer. All right, xy, x-axis, y-axis, my exponential went like this. When I take this and I reflect it over y equals x, I now have a vertical asymptote. So here I have a horizontal asymptote at 0. Here I'm going to have a vertical asymptote at 0. And rather than going through the point 0, 1, I'm going to go through the point 1, 0. My growth is going to start out steep, and then my growth gradually levels off. And it gradually gets more and more and more level, more and more horizontal. Okay? So now my range is all values, but my domain is greater than 0. So here my domain is x is greater than 0. My range is all real values of y. So this, even though it's leveling off, it still does keep going up and up and up and up and up and up. It just takes longer and longer and longer to get up and up and up, but you still approach infinity in your y values. Okay, so if we're in this logarithmic form, the same rules apply for translations. So, for example, if we had something like this, let's say graph, I'm going to go y is less than log base 2 of x plus 3. Okay, well here's what I know. I'm adding 3 inside the function. So as you would expect at this point, it's going to shift us backwards 3. Or in other words, when x is negative 3, my graph is going to behave the same way as without that as when x is 0. So whatever my graph usually will be doing at 0 is now doing at negative 3. Over here, what was my graph doing at 0 when x is 0? That was my asymptote. So over here, I'm now going to have a vertical asymptote at negative 3. So negative 1, negative 2, negative 3. Here's my vertical asymptote. All right. And then as 1 unit over from there is where it crosses, because I don't have any vertical shifting going on. So it's 1 unit over from there across the x-axis. Now it's less than, not less than or equal. So it's going to be a dash. Dash starts steep, goes through, levels off. Okay. Now we need to figure out where should we shade? Well, you can always plug in 0 for xy and see if you get a true statement. Let's see. Is it true that 0 is less than log base 2 of 3? Well, log base 2 of 3, that's the same thing as 2 to what power equals 3, right? 2 to what power equals 3? Well, 3 is bigger than 2. So to get from 2 to 3, we're going to have to raise 2 to a positive integer, which a positive integer will be greater than 0. So that's going to be everything in here is going to be shaded, which also I think you would have anticipated that y is less than is going to give us that. Okay. As a side note, oops, there's the cap. There we go. As a side note, if we had y is greater than, you would shade everything. You would think everything on the opposite side, but we have this asymptote, and this asymptote does block what we're able to shade. And so you would shade up to the asymptote, but not go past the asymptote. Because what's happening there is it's saying we're not allowed to have an x value, because this domain, x is greater than 0, we're not allowed to have an x value of like negative 5. Because if we had a negative 5 here, we would have this going on our right-hand side. We have log base 2 of negative 5 plus 3 is negative 2. And notice we're asking ourselves, 2 to what power equals negative 2? And there's no exponent you can tack on there that will take this positive 2 and raise it to some power to turn it into a negative 2. So we can't shade beyond the asymptote because we're dealing with nonsensical x values that don't work on this graph. Okay? All right. Let me take a quick glance. Other than letting you know what homework problems to do and not do, we can omit some. That will do it for this lesson. Good.